so I'm going to talk about momentum a bit here. And so what we have about momentum is, let's start off with some conceptual stuff. So I have a couple of carts here, and let's just say that these two carts are approximately the same mass, and these two carts are on some sort of track. So if I have these two carts on a track where the one on the left comes in, it's moving to the right, and it hits the second cart, there's two different types of collision. If it comes in and hits and they stick together and then they move together as one unit, that would be known as an inelastic collision. So that is inelastic. That is an inelastic collision, and that is where it's defined as one where kinetic energy is not, at least not all of it, it is not conserved. So kinetic energy is not conserved in an inelastic collision where they stick together. So if you can imagine a scenario where you have, let's say, a very large mass on this object here. So let me group them together. And so it's just sitting there. We have this object coming in, comes in and hits. And if it hits and sticks to it, it'd be like a small car hitting a semi. The two will move together, but they will do so, they will do so together at a very slow rate. So most of the kinetic energy has been lost to things like heat. Versus if we did it the other way around, if we've got this object here coming in from the right, and it hits a very small object, they will move together, and this object will have slowed down only very slightly. So most of the kinetic energy is conserved, even though some of it is lost. So it does matter on the masses, but an inelastic collision is defined as one in which kinetic energy is not conserved. Think of it this way. Usually things stick together in inelastic collisions. All right. Now if we look at elastic collisions, as you can imagine, elastic collisions are ones in which kinetic energy is conserved. So here we've got this object. In fact, a good example perhaps would be if there was some sort of spring at the end of this cart. So let's attach those two together. And so if this object comes in and hits the second, if they are the same mass, then the first one will stop and the second one will continue at the same velocity that the first one was moving at. They bounce off of each other. If they are different masses, so let's say, for example, I take this one and I make it bigger. If this one on the left comes in and hits, this one on the right will shoot off very quickly. So it's just going to shoot off, and the one on the left will continue to move at a relatively slow rate. But in either case, they will bounce off of each other. If we went the other way around, where this one comes in and it hits, it's actually going to even bounce backwards. Think of the extremes. What if the one on the left was so big it was infinitely large, essentially? Then this one would come in and just bounce right back, while this one here would just barely move. All right, so there is some examples in terms of different types of collisions, specifically with elastic and inelastic collisions. All right, so now that we've dealt with that, let's go ahead and look at some math of when these objects are, when they collide and momentum is conserved. So this is the conservation of momentum. In order for the conservation of momentum to be true, that means that we have to have a closed system, meaning that there's no outside forces acting on them. So the friction-free environment, that sort of thing. We're going to say that the momentum of object 1, which is equal to mv. Okay, momentum is equal to mv. In fact, I can just express that as a general statement. So momentum is equal to mv. So the momentum of object 1 is equal to, excuse me, let me back that up. The momentum of object 1 plus the momentum of object 2 is the total momentum of the system. That is going to be equal to the total momentum of the system after the collision. So we're going to say that that is equal to the momentum of object 1 after the collision plus the momentum of object 2 after the collision. So this prime symbol here refers to the momentum after the collision. All right, so since we've established that the momentum before the collision is equal to the momentum after the collision, we can say that this is equal to the momentum total. And this is always true. So this is the momentum total, as is this is also the momentum total. Excuse me. Now that we know that mass times velocity is momentum, we can now substitute in for P1, we're going to put M1 V1. And then for P2, we're going to put M2 V2. So this, again, this right here is the momentum total. So this right here is the momentum total. So we've got this in turn equal to, just give me a second. There we go, that's the way I want it to look. So we're going to say that this in turn equal to the M1 V1 prime. So this is said as prime, so that it's the mass times the velocity of object 1 after the collision, plus M2 V2 prime. Again, V2 prime being the velocity of object 2 after the collision. Sorry about that. So we have the momentum before is equal to the momentum after. And this is for an elastic collision. This is true of an elastic collision. Now let's look at an inelastic collision. So let me just kind of separate these two things. So for an inelastic collision, we can essentially start off the same way, where we say that M1, in fact, let me move that up for you. So this is going to be for an inelastic collision. We're going to say that M1 V1 plus M2 V2 is equal to M1 V1 prime plus M2 V2 prime. Now, that's just where I'm starting. But I want you to recognize, again, if we go back up to the top, remember these two carts. If one object comes in and hits the other, and they stick together and then move together as one unit, we can say that their velocities are equal after the collision. So this becomes unnecessary. We now have V prime is just the same thing for both objects. And the way it's usually denoted is V12 prime. V12 prime, meaning that it's the velocity of both object 1 and 2. We haven't added them or anything like that. It's just the same variable now. And since it's the same variable, we can now express it like this. So that way, M1 V1 plus M2 V2 equals, well, I'm going to factor out the V12 prime and multiply it by M1 plus M2. So if you take a look at it, these are the same thing. I've just pulled out the V12 prime, so that way it's factored out. You can multiply it right back through, so we can just multiply it right back through and get the same thing. And so this is, again, for an inelastic collision. Notice that if you wanted to solve for the velocity of these two objects afterwards, it's actually simpler now than it would be for elastic. And we can just divide each side by M1 plus M2. So separately, I'm going to write these separately, so that way you can, I would like you in your notes to still retain this. So M1 V1 plus M2 V2 divided by M1 plus M2 is equal to V12 prime. So what I've done is I've essentially just divided each side by M1 plus M2, and I've done that to each side. All right, but I want to look at these two equations separately, because by keeping this one like this, you should still recognize that the left side of the equation is the total momentum, the right side of the equation is the total momentum. So again, I can say that this is equal to the momentum total, right? So this is momentum total, this is momentum total. All right, so that is the conservation of momentum. We can apply that. Oops. Let me just write this as total again. There we go. And so you can use this to work out any problems that you need on the conservation of momentum, meaning that momentum is conserved as long as there's no outside forces, no friction. It's a closed system. All right, and before I go, let me tackle one more concept. We have the concept of impulse. Impulse is sometimes in textbooks represented by the letter J, capital J, but often it's just expressed as delta P, meaning that it is the change in momentum. So since it's the change in momentum, think about it, it is mass times velocity. However, it's specifically the change in velocity. So because the mass isn't going to change, but the velocity does. And this is in turn equal to force times time. So to conceptualize this, we're going to say, let's say, for example, we have a baseball pitcher. So let's think about a baseball pitcher. Let me do a really terrible job of drawing a baseball pitcher with his hat. And so he's really taking that big step forward. Here he's probably got a bent leg doing so. He's really taking that step forward. In his backhand, he's got the ball. So here's the ball that's in his backhand, and he's throwing it in this direction. And he's very happy about it. That baseball pitcher is reaching way back and really trying to step through the throw. So that way, from here to here is probably the distance in which the ball is in contact with his hand. That is different than a little kid. Some little kid is going to be throwing the ball, so that way he's just got his arm bent and he's got the ball here, and maybe it's in contact with his hand over a short distance. If you've ever seen a little kid, they just kind of like fling it from their shoulder. And so the difference for the professional baseball pitcher is he is contacting the ball for a longer period of time. He's applying the force, he's applying this force for more time. So it's the same force because he's throwing it as hard as he can. But by increasing the force, he's going to increase the final velocity of the ball. So that is one application of impulse. If I were to apply impulse in another way, I can take a car. This is a lovely car, I know. And so it's moving out to the right, and let's say that this unfortunate car hits some sort of brick wall. I swear that's brick. And so here comes the car, and it's going to hit. Oh, I just meant those to be separate. Not with wheels. No. Gosh darn you, car. All right, so I changed my wall so it has a little bit more perspective to it. So the car comes in, it hits the brick wall, and what happens to the car? Well, the car does a couple things. For one, your hood gets all bent up, and the car almost turns into an ugly accordion in the front. And so that's what happens. Whoops, we want that to be one object. And so the car comes in, and it hits, and it squishes in. It has that crumple zone. And then here is you inside the car. You're unhappy because you got into an accident. And you continue moving because of Newton's first law until you hit something. So it's either the steering wheel or the airbag. Well, the change in momentum for you is the same no matter what. You went from 60 to 0. How you came to a stop might be the difference, but the change in momentum is the same no matter what. So we're going to say that the change in momentum, the change in velocity, and the mass, that's the same no matter how you come to a stop. However, if the car has good crumple zones that allows this front end of the car to really shrink down, that means that it's increasing the amount of time it takes for you to stop, and that decreases the force. If you hit the steering wheel and the car doesn't have good crumple zones, then the amount of time it takes for you to stop is decreased greatly, and the force is increased, causing injury. All right, so that is momentum in a nutshell, including the conservation of momentum and impulse. So if you have any questions, let me know, and let's see if applying, and again, applying this stuff up here is the hard part. Let me just make sure that you guys understand that when you're dealing with elastic or inelastic collisions, that you pay attention to this and do not forget the prime symbol. If you lose track of it, it's a pretty common mistake. All right? So watch out for those mistakes, and you guys have a good one. Let me know if you have any questions.